Hello everyone. Today we are going to discuss the questions in the LeetCode Contest 490. It was the weekly contest. So, let's start. So, what was the first question? The first question is you are given an integer array, nums, where nums of I represents the points scored in the ith game. There are exactly two players. Initially, the first player is active and the second player is inactive. The following rules apply sequentially for each game I. If nums of I is odd, the active and inactive players swap roles. In every sixth game, that is, you are given the indices, the active and inactive players swap roles. The active player plays the ith game and gains nums of I points. You have to return the score difference that is defined as the first player's total score minus the second player's total score. So let me explain you the question. What you are given is you are having two players. So you are having two players, player A and B. Okay. And one of them will be active. Initially, player A is active. Okay. So at each index, you have to process the array sequentially. You are given an array and it contains some values. Okay. Contains some values and based on like how will you decide it, well, like you will go sequentially, like first on this index then on this index. Okay, so what you need to do is these values, whatever the value is, will get added to the score of, initially both have score 0, and these values will get added to the score of the active player. Now how will you decide at the ith index which player is active? Okay, so for that you are given some rules that you have to follow sequentially. Okay. Yeah. So what are the rules? First of all, and you have to process these rules also sequentially. If nums of I is odd, then the active players and the inactive players swap roles. So what is given is, like, suppose 5, 15, 20. Here initially player A was active because it was given like initially player A is active. Now since this value is odd, so the players will have to swap roles. Like the active player will now be B. Now B will be the active player. Okay. So this is the first rule. In every sixth game, that is the indices 5, 11, 17, the active players and inactive players swap their roles. So what is given is like the in every fifth index, like every sixth index, like this is the zeroth index. So like suppose whatever the values may be here. Okay. So 0, 1, 2, 3, 4, 5. Okay. So on the every sixth element, on every sixth index, the active players will swap their role. Okay. So that is another rule. And what is the third rule? Whoever the active player is, he will play the ith game and gain nums of I number of points. Okay. So you have to process these rules sequentially. So what you will do is, this is a basic question. So what we will do is we will go over the array, in increasing order, uh, sequentially, index wise. And first of all, we will check if the value at the ith index is it odd. If it is odd, then simply change the active status, reverse swap the active status. Okay, and if this now this is the first check. Now the second check is if this value, if I mod 6 is equal to 5, because this will let us know like whether this is the sixth index or not, because starting from 4, starting from 0, first index which is the sixth index is 5. Now after this plus 6 becomes 11, so every time you will get mod 5. Now if I mod 6 equal to 5, then swap again, swap active status. Now finally, after swapping, now you have got the active state. Now based on the active state, either add the score to player one score or the player two score, player two's total score. Okay, so that is how it will go. So let's see. Like initially, player one and player two both have 0 score, and we have the active status. Now you can ignore this previous. It has no use. Okay. So if nums of I modulo 2, like if it is odd, then you have to change the active status. And if I modulo 6 equal to 5, then again change the active status. These two conditions are independent from each other, like odd condition and this sixth index condition. So take care of that. Okay. And now finally, if active, I thought like if active is equal to true, then player one is active, and if active equal to false, then player two is active. Okay, so if player one is active, then I have given the score to player one, and otherwise I have given the score to player two. And finally, you needed to return the difference in the score, like player one score minus player two score. So that is what we returned. And finally, this was an easy question. I don't know why it is tagged medium. Okay, so let's come to the second question. Check digitorial permutation. What you are given is you are given an integer n and a number is called digitorial if the sum of factorial of its digit is equal to the number itself. Determine whether any permutation of n forms a digitorial number. Return true if such a permutation exists, otherwise return false. Okay. So what you are given is you will be given an integer n. You are given an integer n. Okay, and suppose 235. Okay, this is an integer. And what you need to find is like you have to calculate the sum of factorial of its individual digits. Like you have to calculate 2 factorial plus 3 factorial plus 5 factorial. Okay, so what is 2 factorial? 2 plus 6 plus 5, 4 factorial I think is 24, 120. Okay, so it becomes 128. Now you have to check like whatever this sum you got, this sum, whatever this sum you got, now whether rearranging the digits of this sum can give you this number 235 or not. Okay, so let me show you what an example would look like. So 145. Let's see n equal to 145. Now what is the sum of these factorials? What is the sum of factorials? So it is 1 factorial plus 4 factorial plus 5 factorial, correct? So what is 1 factorial? 1 plus 4 factorial, I think it is 24 plus 120. So in total 145. So you got NS same, okay. So it is possible, to rearrange these digits. Actually, these are already rearranged, but you could have rearranged them. Let me show you another example if possible. Also, no other example is given. So I hope you got my point. Like you will be given some n. Okay, it will contain some number of digits like 2, 4, 8, 7, like whatever. And based on it, you will calculate the sum of factorials. Okay, and this will give you another number. So, and whatever the sum of numbers you got, you can rearrange the digits of that sum. Like suppose if you have gotten 541 here, suppose although it is not possible, like suppose you got 541. So 541 can be rearranged to 145 still. So still the answer is true because we can still rearrange the digits. Okay. So this is what the question says. So let's see like what can be our approach. So our approach would be like uh, first of all we will calculate the sum, simply calculate the sum using the factorial of sum of digits. So 145 you will calculate 1 factorial plus 4 factorial plus 5 factorial. Okay, so this gives you like whatever 145. Now based on this, suppose this was coming as 541, suppose. Although it will come 145, but suppose for a moment like something 1541 was coming and 145 was to be made. So what will happen here? This is for your understanding. Actually, 145 is coming, but I am saying like condition like this may occur. Like you are given 2, 3, 4. Okay, and in the output you may get 3, 4, 2. Like the sum of factorial, you may get something like this. Okay, so I am just referring to this case like where you are given some n, you calculate the sum. Now, in order for to rearrange these digits into these digits, only we have to check one thing, like the frequency of each element, each digit in n should be same as the frequency of each element in n, in this sum. Like I am saying, frequency of each element in n should be equal to frequency of element in sum. So this is the main condition. So what we'll do simply is, simply count the like simply count the frequency of all the elements in n, and you have calculated the sum. Now simply calculate the frequency of all elements in sum and check like whether these two frequencies are equal or not. So this will be our approach. So let's see. I have created a factorial array to store the factorials beforehand. I am converting this n to a string so that I can know the digits. Like I have to keep track of the frequency of digits also. So and yeah, I have to calculate the sum also. Like this answer is the sum variable. Okay. So what I am doing here is after converting n into string, I am calculating the factorial. Like how factorial of s of I minus 0. So whatever the digit is, I am fetching it and calculating the factorial from the factorials array and adding it in the answer variable, that is the sum variable I told you. Okay, so finally we are converting this answer also to the string, and we are creating the hash table, like calculating the frequency of n and calculating the n was the string s. See, two string of n is equal to s and two string of ans equal to str. So I am calculating the hash table of both of these and checking like if mpp1 is equal to mpp2, then true, otherwise it is false. Okay, so this was another easy question. Uh, you can think of it like it was not too difficult to think. The like only thing here was the implementation, because whatever everything you need to do, it is given in the question itself. Okay, so no problem in that. Yeah, so this was this much only. Okay, so now let's come to the third question. What does the third question states? It is another easy question, I would say. Today's contest was not too difficult. It was an easy contest. The contest was on easy side only. So here is another easy question. Like you are given two binary strings s and t, each of length n. You may rearrange the characters of t in any order, but s remains unchanged. Okay. So return a binary string of length n representing the maximum integer value obtainable by taking the bitwise XOR of s and rearrange t. So what is question 3? Question 3 states you are given two strings s and t. Both are binary strings of same length. Okay. Now, what you need to do is, you can't, the string s remains fixed. S is fixed, and t can be rearranged to however way you like. Okay, so what you need to do is, you need to simply tell us like after rearranging t, what is the maximum s XOR t you can get? You have to maximize this value. You have to maximize s XOR t. Okay, this is what you want to do. So initially, what you are given is, so how will you, maximize XOR? Like when is XOR maximized? When is XOR maximized? So XOR is maximized when, like both like via A XOR B. When will it be maximized? Like the MSB side, the MSB bits are 1. Okay, MSB bits should be 1, and LSB bits also you should like see this one, like MSB one is if this value is set and all of these values are 0, then still this value is greater than this value. I hope you know that. Like a single MSB bit is more valuable than all of the bits to the right, to its right. Okay, so even though all bits are 1 here and only a single bit is 0, still this value is greater, because what is this, 1 2 4 8 1 2 4 8 16. Okay, so Okay, so yeah, so what I was saying is, yeah, so what I was saying is, like the MSB one, here the MSB one, this value, what is this? This is 16 and this is 15. Okay, so a single one in the MSB side is greater than all of the ones value in the right hand side of it. Okay, so that is why your main target to maximize answer is to put is to make sure that ones should appear in MSB sides first. Okay, so our main target in order to maximize the answer will be to uh, what I would say, like in order to maximize, you have to make sure that the MSB sides are getting one. Because suppose you start giving making LSB sides one, so these and you may consume some zeros and ones for that. So, but what our main target is, make sure that the MSB ones like the ones are in the MSB side. Okay, so ones should be in MSB side. Ones should be in MSB side. Okay, so we got our, you know, target, like what we want to do, but how will we do it? Like how, when you can make a one in the, when you can make one anywhere in the answer, like when is the XOR of two values equal to one for a bit, like for one bit, when is the XOR equal to one? It is one when A is not equal to B at that position. Okay, consider A and B as 0 and 1 only. Okay, so when is a particular position, like this was your S, whatever your S was, and some this was your T line. When I can make a one here, like when it will X XOR T equal to one. This will be one when both, like the value at S on this index is not equal to value at S on this value at T on this index. Okay, so in order to make this S XOR T equal to one, I have to put a one over here. Correct. So when can I put a one? For putting a one, T should contain a one first hand. Like suppose initially your T was 0, 0, 1, 1, 0, 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, and 1, 1. Okay, so this was your T. Now what I want to do is, in order to, like, I can rearrange T in such a way that one comes on the first index. Okay, no problem. Now one of the ones is used. Like the one of the ones is used. Now again, I made one here in the S XOR T. Okay, this was our target also. Now again, in order to maximize, see here, here it is one, and now I want to make a one here. In order to make a one here, I want a zero. Like I will see, like, does T contains a zero? Yes, T contains a zero. So I can rearrange so that T can contain a zero here. Okay. Now again see one here. Now I want to make a one here. So does T contain a zero? Yes, T contain a zero. So I will make zero here. Now see again, 0. Now I want to make a one here, so it should contain a one. Does it contain a one? Yes, it contains a one. Also, you need to keep track of the number of ones and zeros you have already put. Like it should not happen. Like although T may contain a one, but the number of ones should not exceed. Like I am saying, like suppose this is the rearranged T you are making. Like I want to say, the rearranged tree should have same number of zeros and ones as in the original tree. Okay, so you have to keep track of the count of zeros and ones. So yeah, let's say now one again comes. So in order to make one, I want a zero here. Okay, so now see three zeros are already used. One, two, three zeros are already used. Okay, so again a one. Now again one comes. Zero again I can put, because this is the fourth and the last is zero. Okay, again one you can put here, but now see again one comes, you don't have a zero over here, so our only option is to put a one here. So one XOR one gives us zero. Again you have zero, so one, and we have an available one. So this is the maximum answer we can get. Okay, Let me take an example from the question also. 0110 and 1110. S is equal to 0110 and T is equal to, let me write it here, T equal to 1110. Okay. So first of all, in order to maximize X XOR T, what I will do, I saw a 0, so I want a 1. Do I have a 1? Yes, I have a 1. So put a 1 here. Now I see a 1. I want a 0 from T. Do I have a 0? Yes, I have a 0. So put a 0. Again, I got 1. Now finally, again I see 1. So do I have another 0? No, there was only a single 0 and that is used. So I have to put a 1 here. 0, I see a 0, I want a 1. So do I have a 1 available? Yes, we have to use two ones and here it was three ones. So I can put a 1. So this is the maximum answer we can get. And you can see this is also given in the answer. Okay, 1101. So this is what our approach will look like. First of all, we will keep track. We will be, doing it in like this. Like when we see a 0 in S, we will look whether we have a 1 available. And if like we have to keep track. Initially, you can hash this. I mean, you can put this in a hash table. Like you can calculate the frequency of zeros and ones. Frequency of 0 and frequency of 1 you can, use. And after you have got this frequency of zeros and ones, now at each step in S, you see like you saw a 0. So do you have a 1? If you do have a 1, then simply put that and subtract the frequency of 1 by 1. Okay. Like do a frequency of 1 minus minus. Okay, if you see a 0, if you see a 1, then simply check like if you have a frequency of 0 greater than 0. If you have, then simply do a frequency of 0 minus minus. And otherwise, if you see a 1 and you don't have a 0 available, like here it was the case, you have a 1 but you don't have a 0 available, then you have no choice, you have to put 1 here only. Okay, and do a frequency of 1 minus minus. So this is another easy question. The only thing you need to know was like where to put the ones in order to make this maximize, and that I told you, like in the MSB side you have to make them ones in order to maximize it. Rest it was implementation only. So see here, uh, MPP of T of I plus plus, we are creating the answer string just as I told you. What is the answer string? uh, So the answer string is this string, like this string, S XOR T. Okay. So this is the string we are constructing. So if MPP of 1 is greater than, if you saw a 0, if S of I is equal to 0 and you have a 1 available, then simply push back 1 and decrease the frequency of 1. And if S of I equal to 0 and 1 is not available, like if MPP of 1 equal to 0, then you have no choice, you have to put a 0 here. Okay. Similarly, if MPP of 0 is greater than 0, simply push back 0. Uh, this is like if S of I equal to 1 in the else part, if S of I equal to 1 and you have 0 available, then simply push 0 and otherwise push 1. And finally, what you need to return was, so you want to return this value, S XOR T. The answer contained this value. I'm sorry, like I told you this. No, the answer contained this T, like the rearranged T. What should be the rearranged T? So this was the answer. In the answer variable, like this answer variable contained this t. Okay, this rearranged t. I'm sorry. Yeah, so this contained this. So this contained this rearranged t. Okay, this was the answer variable in the code. Why this was the answer variable? Because just like here we were seeing, like if 0 is available, like if you see a 0, try if 1 is available, and if not available, put 0. So this was the case, like this was the answer. And finally, in the result, I am storing this. Uh, Finally, in the result, I am storing this S XOR T. Okay. So if S of I is not equal to n S of I, like if this value and this value are not equal, simply push back 1, and otherwise you can push back 0. So although you could have done, I would say you could have done this in this one pass only, but at the time of contest, I didn't think like didn't thought about this so much. I would say so that is why I did this in a separate for loop. Okay, so you could have done this here only. Like you have the answer and this S here, so you could have done this in one for loop only. So this was also another pretty easy question. So let's see this question. This was the only question I would say. It was also like not so difficult, I would say, but just how would you optimize like based on your optimization, like how will you optimize or just a small observation, I would say. So what is the question? Question 4. So you are given an integer array nums and an integer k. Start with an initial value val equal to 1 and process nums from left to right. At each index I, you must choose exactly one of the following actions. You can either multiply val by nums of I, divide val by nums of I, or let it remain unchanged. Okay. After processing all elements, val is considered equal to k only if its final rational value exactly equals k. So you have to return the count of distinct sequence of choices that results in val equal to k. Okay, so division is rational, exact. Okay, not integer division. Okay, so it is saying like, so what you are asked is like you can either multiply val by nums of I, you can either divide val by nums of I, or leave val unchanged. Okay, so and initially your val is equal to 1. So let me explain you the question first. So what does the question say? You are given an array. Okay, so you are given an array like whatever 3, 4, 2, 1, 5, 1. Okay, so you are given some array nums. Okay, and initially you have a value variable like val equal to 1. So what you want to do? Like you will like initially this variable val. Now what you can do? You start iterating sequentially in the nums array. Okay. So now what you can do? You can either multiply this val by nums of I. You can either divide this by nums of I, or you can leave it like you can remain leave it val as it is, and you can go to the next index. Okay. So what are the possible values? Like I can do like after the second operation, I would say. So after here, like see, now I am on this index here. So here I can do a multiply operation like either say multiply, divide and unchange. So initially val equal to 1, like here val was equal to 1. If I multiply it by 3, now val becomes equal to 3. This time here val becomes equal to after dividing, like this is the divide, okay, divide operation. So it becomes 1 by 3. Okay. And here it becomes what? Since I leave it unchanged, so val remains as it is. It remains 1. Okay. Now I am on this index. Okay. In all of them. So let me explain you this case, like what I can do. Again, I have three choices. Either, multiply, divide, or leave it unchanged. Like if I multiply, it becomes 12. If I divide, then it becomes 3 by 4. And, take care, like it was given you that this division is not sealed, like floor division. doing 3 by 4 won't give you 0. It is actually 0.75 only. Okay. So you have to make sure that it is not an integer division. It is the exact rational division, like in the points, or just as given, like in the rational numbers. Okay. So finally, like val equal to 3. Okay. Now, if I leave it unchanged, then val remains 3. Okay. Now I move to this index again. This index again. I have three operations. Uh, I can again multiply. So 12 into 2, 24. Or I can divide. So this time 6. And if I leave it unchanged, sorry. Or if I leave it unchanged, so it becomes 12. Okay. So this is what we are going to do. So at each step you have three operations. Okay. You have three operations. You can do either of three. Okay. And finally, like after iterating over all of the elements, you have to check. Like suppose here in this array, 3, 4, 2, 1, 5, 1. You are also given a k. I will tell you its significance. Like suppose your k was 40. Okay. So now let's do the operation like val equal to 1. Let's create one full sequence of operation. So what I will do, val equal to 1, I will multiply it by 3. Okay, so val becomes 3. Then I will again multiply, so val becomes 12. This time I'll divide 6. This time I'll leave it unchanged. So again 6. Again I will leave it unchanged. So again 6. And again, multiplying, dividing, whatever, or leaving it remains 6 only. So finally the answer came out to be 6. Like the val came out to be 6. So is val equal to k? Like is your 6 equal to 40? No. So you want to do, like you have to count the number of operations, like the number of different operations that will lead us finally so that val becomes equal to k. Okay. So like let me give you an example, a better example. So what I can do. Okay, so this much, and your k was equal to 12. Okay, so starting from val equal to 1, you have to count the number of ways. You have to count the number of ways I can get k equal to 12 finally. Okay, so let's see what are the sequence of operations I can do. So one of them can be like first of all val equal to 1, so multiply by 2. So multiply, so it becomes 2. Val becomes 2. Again you can multiply by 3. So it becomes what? It becomes 6. Okay, again multiply. So again this time this 2 comes. Okay, so I will again multiply. So it becomes 12. Again multiply. 4 comes. I will leave it like unchanged. 1 comes. I will leave it. Okay, so it becomes one of the ways. Okay. Now see another way. What can be another way? Again, I will do a multiplier. 2 into 3, 6 into 2, 3 is 6, 6, 3 is 12. Okay, so leave this 4 unchanged. And this time take this one, like multiply by 1 or divide by 1. So one operation is multiply by 1, another operation. See another, like multiply, 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 divide. Okay, so this is also another operation. So 3. What else can we do? So what else we can do? Okay, so let's do multiply. Okay, 2. So I hope you can see. So multiply. So val becomes 2. This time, okay. So again multiply by 3. So val becomes 6. Okay. So divide by 2 this time. Okay, so divide by 2. So it becomes 3. So and this time 3 multiply by 4. So it again becomes 12. Okay, and this time take one or not take one, or multiply one or divide by one. So this again give you three cases. So what first take, we didn't take it. Okay, so again take this multiply, multiply, divide, multiply, and this time take this like multiply, multiply by one. So again this is one of the case. multiply, divide. So val equal to 2. 2 into 3, 6. 6 divided by, like, see here, 2. First of all, val was 1. So val multiply by 2, it became 2. Val multiply by 3, it became 6. Then we have done a divide here, like see a divide operation. So it again becomes 3. Okay. And this time, this 4. For 4, I again do a multiply operation. Okay, so it becomes 12. And finally, for 1, I will, divide by 1. So 12 upon 1, it is again 12. So again, this operation. So you can see like you are getting many different configuration for getting k equal to 12 finally. So for k equal to 12, you are getting many different configuration. Apart from this, there are many others. Like these are not only this much, but there are many others also in this given example. Okay. So this is what you want to calculate. Like you want to calculate the total number. You want to calculate the total number of ways, or I would say, uh, what I would say, sequence of operations, distinct sequence of operations, total number of ways or distinct sequence of operations you want to do in order to get val equal to 12 k finally, val equal to k finally. Okay, so this is what we want to do. So we have to calculate the total number of ways, or I would say distinct sequence of operations you want to do in order to get val equal to k finally. Okay. So what can be our approach? Like I have told you in previous videos also, like whenever you see options of getting something, like at each step, like you are on a particular state, suppose Q naught. Okay, and at each step, like at Q naught, you have operations, like multiple different ways of going. You can either leave leave it unchanged, leave it. You can either multiply it, or you can divide. And again on these states you have multiple operations. And for this state, like for Q naught, you want some of these values. Okay. And again at this state, this value will be some of these values. For this value, it will be some of this value. So you can see a kind of repeated subproblem here. Like for a special state Q naught, for us for a special state Q naught, uh, for a special state Q naught, you have three ways, and you want to calculate some of these. And again, see this state, like zoom on this particular state. Like if we zoom on this particular state like this, okay, and again you can see here we have three ways. So it is a repeated subproblem clearly. So whenever you see a repeated subproblem, like whatever, like first thing that comes to our mind is DP. Okay, the constraints support. First of all, the thing is if the constraints support. So let's see if the constraints are supporting us or not. So if you see, this nums of I length is 19, and this nums of I is equal to less than equal to 6. And k is definitely greater, like k is 10 power 15. So we can't include k in our state, but we can definitely include the index values or the integer values in the nums array. So how will we calculate? Like what we can do? What can be the states, I would say, for the DP? See, one of the states is index, it is fixed. One of the state is index, like which index we are on. Another state, what can be the another state? So another state can be, you can think like what is the value we are getting at the current index. So one of the state you can think is what is the value we are getting at the current index. Value we are getting at current index. So what I'm saying is, so suppose it was 2, 1, okay. Uh, Okay, so suppose we started with val equal to 1. Okay, so it became 2 here after applying a multiply operation, and again we did a multiply operation here. Okay, so 2. So in order to make it, 12, like I would say, if at this particular index, if at in this particular array, if in this particular array from here till the end, if in this particular array, I am having k equal to 2, like val equal to 2. Like what does dp of I comma val mean? Uh, okay. So let me first write what does dp of I comma val means for you. dp of I comma val mean you are at an index considering like considering the array from I to n minus 1, considering the array from I to n minus 1 with value variable, like with val equal to j, like let me write it as j, with val equal to j, how many distinct sequence are possible to make it, it I would say, to make val equal to, equal to what? Equal to k, finally. Okay. So what does the state says? Let me show you. Like here you got val equal to 2. Till here the val was 2. So I am saying if val equal to 2 here on this particular index, like if on this I, j is equal to 2, like the val is equal to 2, how many number of ways you have in order to get 12 finally? Okay, so there are 0 ways. So like if you have val equal to 2, like you have no operation possible, so that finally you will get k equal to 12. Okay, so you get dp of this 0 1 2, dp of 2 comma 2 equal to 0 here. Okay, so this can be one approach, like this can be one state, like it is valid state. Okay, at each index I, you are asking like if I take this element, so based on that the value gets updated. Okay, the value gets updated. Okay, no problem. And the value gets updated, and you are asking it from the next index. You are asking for the next index, like if val is equal to 2 here, like if val equal to whatever the val here is, if val equal to 2 here, what are the number of ways finally in order to get 12? Okay, so if suppose you leaved it unchanged, okay, if you leaved it unchanged, then val would have remained 1. So val equal to 1. And you are asking on this particular index, like on this particular first index, what are the number of ways in order to get k equal to 12? So you will get like whatever the ways you can get that. Okay. So this can be one of the valid states, like dp of I comma val. This can be one of the valid states. But let's see the problem in directly putting val here. If you directly want to put val here, what is the problems that you will face? So let's see. See, the array size. The array size is 19. Okay, and the value can range from nums of I can range from 6, like 1 to 6. Okay, so the range of val, like in the worst case, in worst case, in worst case, what happens? In worst case, what happens is you will be having like all the 19 elements are 6. Okay, all the 19 elements are 6. Okay, 19 elements are all equal to 6. So in this case, what your val will become? Your val will become 6 power 19. And this is a very large value. You can't make a size like an array of size this large. Okay. And this is the upper bound. Like 6 power 19, you can get like this much. It is very much possible. Like 6 power 19 can appear in an array in some case. Okay. So this is one of the problem. Like what is another problem in this? See, like val it is not necessary that val is an integer only. Like it is not given. It is not given that val is an integer. Val can be rational number also. Val is not equal to integer only. Val equal to rational is possible. Like how is val equal to rational possible? It may happen on an intermediate state, like suppose it was like 4, like 2 and 1 and 4. So on this state, like you came on this state and you thought of dividing by 2. So 1 by 2, it becomes 0.5. Okay, so how will you store, like how will you ask on this state like dp of 1 comma 0.5? Because applying this, the in memory you have to, it is integer only, like the index can be only integer, and you have float values also. So another problem here is like val can be irrational also. So directly putting val is not feasible. So dp of I comma val is correct. Like dp of I comma val, like in the states ahead, I do need to transfer this val variable. But the form, like the correct way of passing it, we have to figure that out. Okay, correct way of passing val in the states ahead. This is what we want to do. Like this is the major part that remains in the question. DP everyone can figure out, and this state also everyone can figure out. But the correct way of transferring this val so that it passes all the like the solution, the questions, test cases is. So what can be one way? Like let's see another way. So I can do like this, like I can pass an array, like in an, well, suppose if there was some way, like here I could have passed an array. So what that array could have contained? It could have contained the powers. Okay, 1, 2, 3, 4, 5, 6, and up to 19. It may contain, it have 19 elements. So this is an powers array. Okay, so each time what I am going to do, I am going to store the power here. Like suppose 2k. Okay, and you want to multiply by 2. So simply increase the power of, this is 0, 1, 2, second index. So simply increase the power by of 2 by 1. Okay, since you thought of multiplying it, so in the overall answer, the power got increased by 1. If you thought of decrease, like plus 1, do a plus 1. If you thought of dividing, then simply do a minus 1 here, minus 1 for divide. And finally, if you have to let it remain unchanged, then don't do anything. Okay, so this is another way. Like instead of passing like dp of I comma val we have. So instead of passing like value here, if there was some way I could have passed a vector here, a vector of size 19. Why 19? I think it is 19 or 6. Oh, it is 6. It is 6. So total 6 elements. Since there are 6 elements, uh, oh, not 6 elements. Since the value in the powers array can be from, since the value in the powers array can only remain from 1 to 6, then this nums array is only from 1 to 6, then the powers can only remain in some multiple of it. Okay. So one of the ways is this, like we pass an array. How we will pass, you can see that. I will tell you that, like how you can pass an array. But first, for a moment, think like if you can pass the powers array. If you could have passed the powers array, then definitely you could have done it. Why? Because this time the floating point issue disappears because we are only tracking powers, and powers are integer values. And another thing here is this because overflow case also won't appear, because at max power of any value would be 19, because the size of array is 19. Okay, so these are the this approach may work. Like we can put a powers array, and each time if you want to multiply by that particular number, increase the power of that number by 1, and if you want to divide, decrease the power of that number. Otherwise, pass the powers array as it is into the next state. So this is one way. Like now you may be asking, how will we pass an array? How will we pass an array? DP of I comma some array. So for that, I tried this approach. I tried this approach because I thought like the constraints were too small. So I thought like it could have passed. Like let me show you. My first approach was this only. I got too much, you know, wrong answers today. So this was the later one. So on this question, I got too much this wrong answers or wrong answers in TLEs only because of this thing only. Like what should be the way to transfer this value variable. So see here, uh, What I'm doing is I'm creating a map. See, a map can help you transfer the information. Map of pair, like the key is map of pair. First of all, it is the index, and second, it is the powers array. Okay, I am passing this powers array and the index. Okay, so and key is the values, like on this particular index, with this as the powers array. What is the answer you can get? Okay, so this I was storing. Like this is the val only. This is the val only. So this I was doing like dp of I comma val. What was the transitions? The transition was dp of I comma val is dp of I comma val I plus 1 comma val into nums of I plus dp of I plus 1 val plus like multiply by that number, leave it as it is, or dp of I plus 1 comma val upon nums of I. Like this was the transition. So this transition I am following here. This was your transition. So this the same, exactly the same transition I'm passing here, but in just in terms of power. Like how? See, so val one is index plus one and powers array, like leaving it as it is. Another thing is you can increase the power of that particular index. So I increase the power and pass the powers array. And next time, since you have increased by one, first of all decrease by one and another decrease. Like you can divide now. So and you have increased the power, so that's why minus equal to 2 here. So again, I passed the powers array. Okay. So this was another approach. So and finally, for this particular index and powers array, you can do val1 plus val2 plus val3. And since map allows us to store, like key can be anything, so that is why I stored a pair of long comma vector, but it gave TLE. I was thinking like I knew that it will give TLE, but I thought like if the test cases were weak, it could have passed. So this was one of my approach. Okay. So now I got to know that I have to optimize. Like first of all, let me tell you why it gave TLE. See, one of the reasons is I am using map. So this map again has a log n factor, and this time since it contains a vector, like pair of vector, so comparison again takes some more time, like length of vector into some log n factor. So it becomes sometimes something like k log n, I would say, where k is the size of this array. So 6 log n, something like this. So it you use some operations. Another this operation consuming, like time consuming thing in the code is this powers array. Each time I am copying the value. So this also is taking much operations, and this mpp dot find, again it will take some operations, like inserting, finding, everything is taking too much operations. Okay. And see here also, in this code, like what I'm doing is first I am calculating this, like if this make, like initially val was 1, I am iterating over the powers array, and I am calculating what will finally make be. Okay. So and I am returning if make is equal to k, then return that, return 1, otherwise you have to return 0. So this was what I was doing. So since we know it gave TLE, what can be our optimization? So see carefully. What I saw was like, do I need to actually store this full thing, like the power of all elements? Do I actually need to store the power of all elements? Think in terms of number theory. Like, do I actually need to store the power of all elements? We know that any number can be stored. Any number can be stored in terms of prime factors. In terms of prime factors, correct? So this was my second approach. Like I thought I would transfer all of this val array. Like since the val array is this powers array is getting large. Powers array is large, of size 6, I would say. So how can I reduce this powers array? If you see from 1 to 6, what are the prime factors of any number? 2, 3, 4, 5, 6. One doesn't matter, but anyway, let's take it. See, 2 has 2 into 1. The prime factors are 2. Prime factors are 3. It has 2 power 2. It has 5. And it has 2 into 3. So how many distinct prime factors did you get? 2, 3, and 5. Okay. So 3 distinct factors. Correct. So 3 distinct factors are there. So what you need to do is, instead of passing an array of size 6, instead of passing an array of size 6, you can simply, pass three distinct factors. Like three distinct factors are enough, like power of 2, power of 3, and power of 5 in the current number. Because we are always sure that the answer, if possible, will only be in power of 2, 3, and 5, because the nums array only contains the values from 1 to 6. Okay. Since the nums array contains the value from 1 to 6, I am sure that the whatever the number be, it can be represented in form of 2, 3, 5 powers, because these are the prime numbers. These are the prime numbers, and since we know that the value, like the value will be power of these numbers, and these numbers, like I am saying is, you may say like the number can be 5 power 2 into, like, suppose what, 125 into 4, I would say. So how much is 125 into 4? Is 500. Suppose it is 500. Okay. You may say the value is 500. Okay. The value can be 500. But you can write it like this: 5 power 2 into 2 power 2. So at last, if the value is constructed from the nums array, it will contain powers from anything like 1, 2, 3, 4, 5, 6. And these may have some powers, like these may have some powers. Okay, so finally, and we already know, like these numbers themselves can be represented only in terms of 2, 3, 5 powers. Okay, so finally, what conclusion remains is, we can always represent the val in powers of 2, 3, 5. Okay, so these are the only three variables I need to keep track of, like the power of 2, power of 3, and power of 5. Okay, these are the only three things that I need to keep track of. Okay, so our search space got reduced again. Like this earlier, we were transferring the whole array. So this time, definitely, we have done some optimization. And since there are only three values, we can pass them in form of variable also. Like earlier, we were doing a vector. Earlier, we were passing a vector that was copying. We needed to use like a map for transferring this vector. But this time, since we have only three values, 2, 3, 5, we can definitely we can definitely pass them as variables. Okay, so three states. Apart from index, we got three states, like power of 3, 2, 3, and 5. So this time we get dp of index, and since it was the value. So this time val gets expanded. Val gets expanded to what? It gets expanded to power of 2, power of 3, and power of 5. Together these are still val only. Together these are still remain val only. But see, together they are still equal to value only. But only they have expanded because it contained the problem of that floating point and overflow error. This time we are sure it won't overflow. So let's calculate the ranges of these power of 2, power of 3, and power of 5s. Okay, so at max, like it may happen all of the values contain 4, like 4. So 4, because 4 contain two factors, like 2 power 2. Okay, so and all the 19 elements may contain this 4. So 2 into 19. Okay, so 38. Maximum value I can get is 38. What is the minimum value I can get? I can get minus 38 if I divide by all fours. Okay, so for 2, the range gets minus 38 till 38. Okay, for 3, what can happen? It can range from how much? Like it will range from all the values can be 3. Okay, so it will range from minus 19 to 19, because all the 19 elements can be 3. Similarly, for 5 also, it will range from minus 19 to 19. Okay, so these are the ranges. So since we want to, inside the index, power 2, power 3, power 5, you may get negative also. So we have to definitely add some offset, like in order to, definitely add some base value. So see, the total values I will get here is 76. Here it is 38. I'm right. Yeah, 38. Here it is also 38. So you can, and it should happen like minus 38 should correspond to 0, because we can't store minus value in this. Like minus value, you can't store minus this negative value in the array index. Okay. So that is why we are adding some offset. I hope you know this offset thing. Like we can, map like everything, like adding minus 38 plus 38. Everything will be, increased by 38. So minus 38 becomes 0 and 38 becomes 76. 38 becomes 76. And similarly, minus 19 should correspond to 0 and 19 should correspond to 38. Like anything positive, definitely, like not definitely 0, like it can be any value, but it should be greater than equal to 0 because we want to put it in the index array. Similarly for 5 also. This is for 2, this is for 3, and this is for 5. Okay. So minus 19 should correspond to 0, or I would say greater than 0, and it should correspond to what? 38 again. Okay, so we have to keep track of this offset thing also. Like, so this I think you should know. Like in the DP, whenever you see like negative states, like negative index, you have to add some offset to it in order to get to positive indexes only. So this is what our approach will look like. Okay. So at each step, what you will do is you will simply keep track now. Simply you come at an index. Suppose it contains 4. Okay, 4. Suppose it was the first value. So you thought like I would multiply it. So simply, increase the power of 2 by plus 2. Okay. And if you thought like I will divide, then simply decrease the power of 2 by minus 2. And keep track of the offset thing. Okay. Before updating, I will show you that in code. Now see if 6 comes, if 6 appears. If 6 appears, what will happen? See, if 6 appears, what will happen? You will simply need to, either add power of 2 by plus 1, like 2 for 2 you have to add plus 1. If you thought of multiplying, then simply increase power of 2 by plus 1 and simply increase power of 3 by plus 1. And similarly here, if you want to do like divide by 6, then simply minus 1 of power of 2 and minus 1 of power of 3. Okay, this you can do. So this time we are definitely sure that this won't give TLE because the range only gets from like index is from 19. So 19 into somewhere you can say 80 into 40 into 40. So how much is this? You can see 1, 2, 3. Okay, so uh 2 power 3, 4, 5, 6, 7. 2 power 7 into 10 power 3. So this is 1e6, somewhere about 1e6 into 19. Okay, so it is somewhere around 1e7. Okay, big of 1e7, or I would say 2